Hey everyone, and welcome back to the channel. Have you ever looked at the periodic table and wondered about those two huge chunks of elements right in the middle and at the bottom? The ones that seem to hold the key to our most valuable and industrially critical materials? We are talking about the D block and the F block elements. In this video, we're diving deep into what are commonly known as the transition metals and the inner transition metals. These elements, from the iron in your blood and the copper in your wires, to the rare earth elements in your smartphone and the gold on your jewelry, are absolutely essential. So, hit that like button, subscribe if you haven't already, and let's unlock the chemistry of the D and F block elements. The D block elements occupy the large central region of the periodic table, placed between the S and P blocks. In these elements, electrons begin to enter the D orbitals of the penultimate, or second-last energy level. This creates four transition metal series: 3D, 4D, 5D, and 6D. Their general outer electronic configuration is N-1D 1 to 10, NS 1 to 2, with a few important exceptions. Because the energy difference between the N-1D and NS orbitals is very small, some elements achieve greater stability by having half-filled or fully filled D orbitals. This is why chromium has the configuration 3D5 4s1 instead of 3D4 4s2, and copper has 3D10 4s1 instead of 3D9 4s2. Elements like zinc, cadmium, mercury, and Cn have completely filled configurations, so they are not considered transition elements. Because D orbitals extend further out than S or P orbitals, they strongly interact with their surroundings, giving transition elements many unique properties. These include variable oxidation states, formation of colored ions, complex formation with ligands, catalytic activity, and paramagnetism. Transition metals show more similarities across each horizontal period, though some group-wise similarities also exist. In this chapter, we explore these general trends, focusing first on the 3D series. The elements of the first transition series show strong and consistent trends that help us understand the entire D block. Transition metals generally exhibit classic metallic properties. They are strong, hard, malleable, ductile, and excellent conductors of heat and electricity. Except for a few like zinc, cadmium, mercury, and manganese, they also have typical metallic crystal structures at room temperature. One striking feature of transition metals is their very high melting and boiling points. This happens because both their N-1D electrons and NS electrons participate in metallic bonding, making the bonds between atoms very strong. Across each series, melting points usually increase and reach a maximum near the D5 configuration, and then slowly decrease as the atomic number rises. These metals also have very high enthalpies of atomization, meaning a lot of energy is needed to separate their atoms. This again reflects the strong bonding present in these elements. Metals with very high atomization enthalpy tend to be less reactive and show more noble character. Another key trend is that the second and third transition series have even higher atomization enthalpies than the first series. This is the reason why heavier transition metals often form compounds with direct metal-to-metal bonds. Across any transition metal series, ions with the same charge become smaller as we move from left to right. This happens because each step adds one proton to the nucleus and one electron to a D orbital. Since D electrons do not shield each other effectively, the increasing nuclear charge pulls the outer electrons closer, reducing the ionic radius. The same pattern is seen in atomic radii, though the change within a single series is quite small. A more interesting trend appears when we compare atomic sizes across different series. The second transition series has larger atomic radii than the first, as expected, but the third series does not get bigger. Instead, the 5D metals have almost the same radii as the 4D elements. This unusual behavior is due to lanthanoid contraction. Before the 5D series begins, the 4F orbitals are filled. Because 4F electrons provide very poor shielding, the increasing nuclear charge pulls the electrons inward, causing a steady decrease in size across the lanthanoids. This contraction cancels the expected size increase in the 5D metals. As a result, elements like zirconium and hafnium have nearly identical radii and show remarkably similar chemical behavior. Additionally, as atomic radii decrease and atomic masses increase across the series, the densities of the transition metals tend to rise, which is clearly seen from titanium to copper. Across each transition metal series, ionization enthalpy gradually increases from left to right. This happens because the nuclear charge keeps increasing as electrons fill the inner D orbitals. However, unlike the sharp rise seen in non-transition elements, the increase in ionization enthalpy within a transition series is much smaller. This is because 3d electrons shield the outer 4s electrons more effectively than outer electrons shield one another, so the pull on the outer electrons doesn't increase dramatically. As a result, atomic size decreases only slightly, and the first ionization enthalpy rises slowly across the 3d series. When these elements form ions, the 4s electrons are removed before the 3d electrons, so the pattern becomes clearer in the higher ionization enthalpies. The second and third ionization enthalpies generally increase across the series, but there are notable breaks at Mn2+ and Fe3+, because both ions achieve the especially stable d5 configuration. This stability arises from exchange energy, which is highest when electrons occupy separate degenerate orbitals with parallel spins, as seen in half-filled configurations. Because of this effect, removing an electron from a stable d5 or d10 arrangement requires more energy. This explains why chromium+ and copper+, which already have d5 and d10 configurations, show unusually high second ionization enthalpies, while zinc shows a lower value due to the easy removal of a 4s electron. The third ionization enthalpies are even higher because they involve removing electrons directly from the d subshell, making it particularly hard to disturb the stability of d5 and d10 ions. Ultimately, although ionization enthalpies help us predict the stability of oxidation states, the pattern is complex and influenced by many factors, including nuclear charge, shielding, and exchange energy. A key hallmark of transition elements is their ability to show a wide range of oxidation states. In the first transition series, this variation is especially clear. Elements in the middle of the series display the greatest number of oxidation states, manganese being the best example, with oxidation states ranging from +2 to +7. At the two ends of the series, the range becomes limited. Early elements like scandium and titanium have too few d electrons to show many oxidation states, while later elements like copper and zinc have almost filled d orbitals, leaving fewer empty orbitals for bonding. This is why zinc shows only the +2 state, and copper commonly shows +1 and +2. Up to manganese, the maximum stable oxidation state equals the total number of available s and d electrons, as seen in species like TiO2, VO2+, CrO4 2-, and MnO4-. Beyond manganese, higher oxidation states become less stable, so the common oxidation states shift towards +2 and +3, as observed for iron, cobalt, nickel, and copper. Another important feature is that oxidation states in d-block compounds often differ by just 1 unit, because electrons are being removed one at a time from closely spaced d orbitals. This behavior contrasts with non-transition elements, where oxidation states typically differ by 2. Across groups 4 to 10, heavier transition metals tend to show higher oxidation states more readily. For instance, molybdenum and tungsten in +6 states are more stable than chromium in +6, making dichromate a strong oxidizing agent, while MO3 and WO3 are not. Very low oxidation states can also appear when ligands capable of strong pi backbonding are present, as in metal carbonyls like nickel tetracarbonyl and iron pentacarbonyl, where the metals exist in the zero oxidation state. The behavior of transition metals in redox reactions is closely linked to the transformation of solid metal atoms into M2+ ions in solution and the corresponding standard electrode potentials. Copper stands out in this series because its E0 value is positive. This means copper does not liberate hydrogen from acids the way other metals do. Only strong oxidizing acids like nitric acid or hot concentrated sulfuric acid can react with copper. The reason is simple. Converting copper solid to copper 2+ aqueous requires unusually high energy, and this is not compensated by its relatively low hydration enthalpy. Across the series from titanium to zinc, the electrode potentials gradually become less negative. This trend follows the increase in the sum of first and second ionization enthalpies. Still, some elements like manganese, nickel, and zinc show more negative values than expected due to additional stabilizing factors like hydration enthalpy or stable electronic configurations. A classic question arises when comparing chromium 2+ and manganese 3+, both of which have a D4 configuration. Chromium 2+ acts as a strong reducing agent because losing an electron leads to a more stable D3 configuration with a half-filled T2G level. In contrast, manganese 3+ is an oxidizing agent because gaining an electron results in the highly stable D5 configuration. In short, chromium prefers to get oxidized, while manganese prefers to get reduced. Looking at the M3+ over M2+ electrode potentials, we see more trends. Scandium shows a very low value because Sc3+ has a noble gas configuration and is extremely stable. Zinc shows a very high value because removing an electron from zinc 2+ means disturbing the stable D10 configuration. Manganese has a comparatively high value, reflecting the exceptional stability of manganese 2+ with its D5 configuration, while iron shows a lower value as Fe3+ also enjoys D5 stability. These trends continue in the halides formed by transition metals. The highest oxidation states appear in compounds like TiX4, VF5, and CrF6. Fluorine, due to its high electronegativity and strong bonding ability, can stabilize these high oxidation states very effectively. For manganese, the +7 state appears not in simple halides, but in compounds like MnO3F. As we move past manganese, simple trihalides become uncommon except for FeX3 and COF3. Lower oxidation states often show instability in fluorides. For example, VX2 and CuX are unstable. By contrast, copper-2 halides are well known, except CuI. Here, copper-2 actually oxidizes iodide to iodine, forming CuI in the process. Copper-1 in aqueous solution is unstable and undergoes disproportionation into Cu2+ and Cus. The reason is that Cu2+ is much better stabilized by hydration enthalpy than Cu+. Oxygen stabilizes high oxidation states even more strongly than fluorine. In the oxides, the maximum oxidation number for each metal corresponds exactly to its group number from Sc2O3 up to Mn2O7. Beyond group 7, higher oxides do not form. For example, iron cannot go beyond Fe2O3, although ferrate 6 ions exist briefly in alkaline solution before decomposing. Oxygen's ability to form multiple bonds and strong M-O interactions explains this superior stabilizing effect. Highly oxidized oxocations like VO2+, VO2+, and TiO2+ are also common. In compounds such as Mn2O7, each manganese atom is surrounded tetrahedrally by oxygen, forming structures like the well-known tetrahedral MO4N- ions of V5, Cr6, and Mn in its highest oxidation states. Transition metals show a wide range of chemical reactivity. Many of them dissolve in mineral acids because they are electropositive, but a few behave like noble metals and remain unaffected by simple acids. In the first transition series, almost all metals except copper react with hydrogen ions and get oxidized, although the speed of reaction varies. In fact, titanium and vanadium hardly react with dilute non-oxidizing acids at room temperature because they become passive. Across the series, the tendency of metals to form M2+ ions gradually decreases. This is reflected in their standard electrode potentials becoming less negative from left to right. The reason behind this trend is the steady increase in the sum of the first and second ionization enthalpies. However, manganese, nickel, and zinc interrupt this smooth pattern. Their E0 values are more negative than expected. Manganese shows this deviation because its M2+ ions have stable electronic configurations, D5 for Mn2+, and D10 for Zn2+. In the case of nickel, the unexpectedly negative value comes from its very high hydration enthalpy. Now, if we compare the redox couple M3+ to M2+, the strongest oxidizing ions in aqueous solution are Mn3+ and CO3+. On the other hand, Ti2+, V2+, and Cr2+ act as powerful reducing agents. They can easily donate electrons and even liberate hydrogen gas from dilute acids. When a magnetic field is applied to a substance, we mainly observe two types of behavior, diamagnetism and paramagnetism. Diamagnetic substances are pushed away by the magnetic field, while paramagnetic substances are pulled towards it. Some materials are attracted extremely strongly. These are called ferromagnetic. Ferromagnetism is simply an intense form of paramagnetism. Most transition metal ions show paramagnetism. The reason is simple. Paramagnetism arises from unpaired electrons. Every unpaired electron carries a magnetic moment due to its spin and orbital motion, but in the first row transition metals, the orbital contribution is almost completely suppressed, so only the spin matters, and we use the spin-only formula to calculate the magnetic moment. Mu equals the root of n into n plus 2, where n is the number of unpaired electrons and mu is measured in Bohr magnetons. Just one unpaired electron gives a magnetic moment of 1.73 bm. As the number of unpaired electrons increases, the magnetic moment also increases. That means the magnetic moment of a substance gives a direct clue about how many unpaired electrons are present in that atom, ion, or molecule. The magnetic moments calculated using the spin-only formula match very well with experimental values from many hydrated ions of the first row transition elements. When an electron in a transition metal ion jumps from a lower energy d orbital to a higher energy d orbital, it absorbs light to make that jump. The energy gap between those two d levels matches the frequency of the absorbed light, and this frequency usually falls in the visible range. Whatever color the ion absorbs, the opposite color is what we see. This is why most transition metal ions are beautifully colored. The exact color depends on the ligand, because ligands decide how big the d-d energy gap is. In water, for example, Ti3+ looks purple, V4+ looks blue, Fe3+ appears yellow, CO2+ looks pink, Ni2+ appears green, and Cu2+ shows a deep blue. Transition metals love forming complexes. They easily bind with ions or molecules around them because their ionic sizes are small, their charges are high, and their empty d orbitals are available for bonding. Transition metals are excellent catalysts. Why? Because they can switch between multiple oxidation states, form temporary complexes with reactants, and weaken reactant bonds at their surface, lowering activation energy. Examples: V2O5 in the contact process, Fe in the Haber process, Ni in hydrogenation. Small atoms, such as H, C, and N, can slip into the gaps inside metal lattices. These are called interstitial compounds, like TiC, Fe3H, or Mn4N. They typically show very high melting points, extreme hardness, metallic conductivity, and strong chemical inertness. When metals mix, they form alloys. Transition metals easily form alloys because their atomic sizes are similar. These alloys are strong, hard, and often have high melting points. These alloys form the backbone of countless industrial materials. Iron and steel remain the backbone of modern construction because their production efficiently combines the reduction of iron oxides, removal of impurities, and the controlled addition of carbon and alloying metals such as chromium, manganese, and nickel to enhance strength and durability. Several metal compounds are manufactured for specialized applications. For instance, titanium dioxide serves as a major white pigment, while manganese dioxide is widely used in dry cell batteries. The battery industry also depends heavily on zinc and nickel-cadmium systems. Group 11 metals still carry the traditional name coinage metals, although today silver and gold are mostly used for collectible coins, and even copper coins in the UK are now copper-coated steel, while their silver coins are actually copper-nickel alloys. Many D-block metals play a crucial catalytic role in industry. Vanadium 5 oxide drives the oxidation of sulfur dioxide during sulfuric acid manufacture. Titanium tetrachloride with trimethyl aluminum forms Ziegler catalysts for producing polyethylene. Iron catalysts are fundamental to the Haber process for synthesizing ammonia, and nickel catalysts make the hydrogenation of fats possible. The Walker process relies on palladium 2 chloride to oxidize ethine to ethanal, and various nickel complexes help polymerize alkynes and aromatic compounds such as benzene. Even the photographic industry is built on the light-sensitive behavior of silver bromide, demonstrating once again how indispensable the D-block elements are across technology and industry. And that wraps up today's exploration of the D-block world, where metals aren't just shiny, they're the hidden engines behind industries, reactions, and everyday technology. If this video helped you see chemistry with a little more clarity and curiosity, make sure to like, share, and subscribe. Your support helps me bring more high-quality, student-friendly science content right to you. Drop your questions or next chapter requests in the comments. I'm always listening. Until then, stay curious, stay consistent, and keep learning. It's RJK signing off.